Today's topic is appearance issues in Moldflow. Let's start with knit lines. Blemish that occurs from the collision of two flow fronts coming together. It can reduce the strength, it can be unsightly, and it's often unavoidable due to the geometry features like the one you see here. You have a hole in the part. This also occurs oftentimes on tall standing cores. This is an example. This is a riding mower. And when they started molding parts, they saw this giant knit line that was very unsightly. And in some cases, you can get away with, molding the part with the hole filled and then maybe punch or machine the hole later. But this was such a big hole that wasn't really an option. So we had to see what we could do to place the knit line in an acceptable area. So can we move the gate? In this case, that was not an option. Maybe you can resequence the flow. Maybe not. If you have valve gates, then that's a possibility. Maybe modify the part design, and that is the route we chose in this case here. So we used flow leaders and flow restrictors. So next on the list is air traps. Air traps are formed because air that occupies the mold that should get out as plastic flows doesn't. It's supposed to be able to vent the air through vents. So the part design, gate position can produce these backfilling or racetracking effects. They can cause non-fills, or they could possibly actually burn the material. That burned material comes from compressed air. That volume of air gets compressed as backfilling occurs. Compressed air leads to higher temperatures. Then you might see a burn mark on your part. In the case of short shots, it's the compressed air pushing back the buildup of pressure in that area, pushing back on the melt enough to keep it from filling. So here's a case of an air trap in an existing mold. It wants to fill the thick sections, and it fills them very easily, but meantime, some of the material gets into these thin sections and starts hesitating. So mold was already built. We came up with the idea of filling a little bit faster. Keeps the material warmer longer so that it doesn't hesitate quite as much in the cannula, and allows it to fill out. One of the ways to fix things is through a vacuum venting system. This is an aside from Moldflow, but this is a product we sell called the Mold-Vac. So before and after, you can see, if you're absolutely stuck and you've built the mold and you have this backfilling kind of condition, you can fit the mold for these Mold-Vacs and pull a vacuum on it to get the air out of there so that it doesn't compress and superheat and cause short shots and so forth, or burns. This was another case for an existing tool. We had a part design change in this case. This air trap in the optical area was unacceptable. So we increased the wall thickness in that optical area as much as they would allow it. So the air trap was moved to an acceptable area. Next on the list here is sink marks. It's a depression at the surface where the backside features intersect. Sometimes happens in very thick sections where there's not kind of an intersection on the backside. This is caused by excessive shrinkage. That's essentially what a sink mark is. Usually in thicker sections, farther from the gate, forming at higher temperatures perhaps, so cooling can play a role in that as well. Higher strength materials, of course, are more susceptible to this phenomenon as well. And then, like I said here, beware of the corners. So on an existing tool, improving sink, you're kind of at the mercy of the design at this point. But you definitely want to check your processing. Do a gate freeze study, number one. Again, there's not much you have at your disposal, but I've seen it happen where you go back and try to reduce the rib to wall ratio. So major tool modifications generally need to be made in those situations. Maybe some welding. Increasing pack pressure, that's another process fix. Problem with that is now we're making ourselves more susceptible to the clamp force requirement. Moving gates, this may or may not be possible, and it could cause unintended consequences. So if it's a new tool, obviously you want to try to use the simulation results. Best solution is to reduce the rib to wall ratio. Obviously no welding involved because we haven't made the tool yet. A lot of folks like to use sink savers where they thin out the area closest to the intersection with the main wall. But you got to be careful with that because you got to be aware of short shots. Again, moving gates closer to the areas of sink is important where we can. The number we try to stay below is 0.1 millimeters, and if there's glossy finishes, we go about 1/4 of that. Next issue is gate blush. It's a blemish extending from the gate. It's caused by material degradation, where we have excessive shearing, breaking molecular chains. Usually occurs thin gates, small gates, molds with too few gates, perhaps the fill rate is too fast. Here's just a quick example of changing gate size. You could slow down the fill speed. Again, that could cause some unintended consequences. It's typically best to increase the gate size. That may or may not be undesirable from an aesthetic standpoint if it's leaving a large gate vestige. Larger gates could also cause some sink issues near the gates as well. So for new tools, again, you use simulation results. You want to ensure the proper number of gates. Increasing gate size, I already mentioned. Ramp speed profiling is another way to go. Again, the best solution to all this is avoidance. So make sure your part is feased. You know, we do feasibility studies here at CAE. These feasibility study assures us that the part is good for tooling. You know, it's sufficient sidewall draft, for example. But the big one, you know, for appearance issues and sink marks and so forth, particularly rib to wall ratio. So it's good to do these feasibility studies to catch some of these issues before they even start. So some parting thoughts here. So use simulation up front before the mold is built. I'm a big fan of hardwiring solutions into the part of the mold design. Use expert Moldflow engineers. I don't care if it's us or your own. Their expertise is going to help us know when the results are reasonable, whether or not we've got good material data. You know, can we trust the results we're getting because we've got good material data? Do we have the right mesh? The engineers are going to know how to identify the causes by using Moldflow and how to solve those problems through mold and part design, or if it comes down to it, how to process it